Right, on to, I forget, is this video 4 or video 5? I think it's number 4. Alright, on to part 4 of the exam key. Okay, we are on number 12 now. How did Rutherford explain the results of the gold foil experiment? Alright, the first observation. Most alpha particles were not deflected at all when passing through the gold foil. Well, that's because most of the atom is empty space. Now, that was really all that you had to say to get 2 points. I think that some folks got a little confused and started talking about like electrons and in that empty space, and that's something maybe you remembered from high school. It's not something that we really talked about yet, and so I sort of gave you credit unless you said something that was blatantly incorrect if you started talking about electrons. But really the reality is that most of the atom is just empty, and so it just passed straight on through. These alpha particles did. All right, look at B. Some alpha particles exhibited backscattering, that is, they bounced back towards the particle source. All right, so the reason why is that the alpha particles hit the positively charged massive nucleus head on, or something to that effect. I really wanted you to talk about how the nucleus was positively charged, because alpha particles are also positively charged, so that has an effect too. There was that electrostatic repulsion. And also I wanted you to say something about the fact that the nucleus is massive, or that it's really dense. 2 points there. Great. All right, on to 13. How many hydrogen atoms are contained in 8.34 grams of ammonium benzoate? And there's our formula right there. Okay, so we want to calculate hydrogen atoms. So the first thing that we're going to have to do is go from grams to moles, and then from moles to molecules, and then from molecules to numbers of atoms. All right, so here, let me move my iPad a little bit. There we go. So let's set this up. First step, moles to molecules, or excuse me, grams. I'm getting confused here. Grams to moles. 8.34. It's too many phone calls, too many interruptions I'm getting. 8.34 grams of ammonium benzoate, H5COO and H4. All right, my molar mass, 139.2 grams, C6H5, OO and H4 to 1 mole. Now on the exam you didn't have to write all this down, I'm just doing it. I like to do it for myself and also just for clarity for folks watching. On the exam you didn't have to write these formulas here. Alright, so I've gone from grams to moles. Now I can use Avogadro's number to go from moles to number of molecules. 1 mole, C6H5COO H4 to 6.02 times 10 to the 23rd molecules, C6H5COO and H4. Okay, so now I've gone grams to moles, moles to molecules. Now I need to go from molecules to number of hydrogen atoms. The way I'm going to do that is I'm going to have 1 molecule, C6H5COO and H4. In 1 molecule of ammonium benzoate, I have got 5 plus 4, 9 atoms of hydrogen. So I should get 3.25 times 10 to the 23rd atoms of hydrogen. Sweet. All right, that was 8 points. I think most people did that fairly well. At least they did part of it fairly well. I think people got confused at this point. This last conversion, I think, was where some folks kind of got turned around. Okay, moving on to number 14. Oxaliplatin is a chemotherapy drug used to treat colon cancer. It's kind of an interesting class of drugs that uses metals as part of their structure. All right, we're given the formula here, and we want to know what the percentage is of platinum by mass in this drug. So the first thing we're going to do is find the molar mass of the whole thing, and then we're going to find the using the periodic table, we'll find the atomic weight of platinum, and we'll just divide to get the percentage. All right, so step 1, molar mass of ox. I'm just going to abbreviate it like that. Now, I'm not going to write out how we calculate this. We use the periodic table and these atomic masses, and we should get 397.3 grams per mole. Again, I'm going to 1 decimal place. If you go to 2, that's totally fine. More than 2 is really overkill, but 1 or 2, you're good. Okay, so I've got 397.3 grams per mole. My atomic mass of platinum is equal to 195.1 grams per mole. All right, so to find the percentage of platinum by mass, I'm going to take my mass of platinum, 195.1 grams platinum, and I'm going to divide it by 397.3 grams total. Multiply that by 100%, and I should get 49.1% platinum in that drug by mass. Now, if in your answer you included 2 or 3 decimal places, I gave you credit for it because there's really, no significant figures here. But just, to reiterate, really 1 or 2 decimal places is all you need to go to. 3 or 4, totally not necessary. All right, on to number 15. 15. Here we go. We are writing and balancing a chemical equation for the reaction of lead nitrate solution. I see the word solution. That tells me that things are aqueous. And potassium iodide solution, which forms solid lead iodide and potassium nitrate solution. Okay, so first step in writing a chemical equation, let me write my reactants. I have lead nitrate. I'm told it's lead 2+. Nitrate is NO3-. So I have to have 2 nitrates. I'm also told this is a solution, so it's aqueous, plus potassium iodide. Potassium is 1+, iodide's 1-. So potassium iodide, also aqueous from the solution. All right, my products, solid lead iodide, lead 2+, iodide 1-, so I have to have I2 solid, plus potassium nitrate, +1, -1, KNO3 solution, so it's aqueous. All right, so you got 1 point for each formula. You got 2 points for having all your states correct, and now we need to balance this equation. All right, so I see here already, just right off the bat, I need to have 2. Oh, shoot. Sorry. I was going to write that here. My bad. 2. I need 2 iodines on this side to match the 2 on this side. Okay? I've got 2 iodines, sweet. 1 lead, that's great. 2 nitrates. Ooh, 1 nitrate. Let's go ahead and fix that. 2 nitrates, 2 potassium. Now I'm balanced. Great. Okay, on to number 16. Valproic acid. This should look familiar to folks. I think this was a homework problem that I threw on there. All right, valproic acid is composed of C's, H's, and O's. A 0.165 gram sample is burned in a combustion chamber. The gain in mass of water is 0.166. CO2 absorber 0.403. What is the empirical formula? All right, first thing we're going to do is we're going to find grams of hydrogen and grams of carbon. However much carbon and hydrogen were produced had to come from the sample. That was the only source of carbon and hydrogen. So if we find grams of those guys that were in the products, that's how many was in the reactant. Okay, so that's our first step, is to find grams of hydrogen and grams of carbon. So grams hydrogen, 0.166 grams H2O. I'm starting with my H2O. And I'm going to go from grams of H2O to moles of H2O. I can't go directly from here to grams of hydrogen. All right. For every 1 mole of H2O, I have 2 moles of hydrogen. That was a place where a lot of folks struggled. And every 1 mole hydrogen has 1 gram for its molar mass. So I get 0.0184 grams hydrogen. I'm playing a bit fast and loose with significant figures here because ultimately I'm looking for an empirical formula, so it's not going to be that big of a deal. I should have 3, I guess I'm doing okay. I have 3 sig figs. I have 3 sig figs here. But, you know, if you want to include some extra numbers, it's not going to be a tragedy. You didn't get counted off for it on the test. All right, grams of carbon, 0.403 grams CO2. I'm just doing the exact same thing that I did before. 44 grams CO2, 1 mole CO2. 1 mole CO2 gives me 1 mole carbon. 1 mole of carbon gives me 12 grams of carbon. So I'm left with 0.110 grams of carbon. Sweet. All right, so I have how many grams were produced. That's how many grams were my products. That's how many grams have to have been in my reactants. To find grams of oxygen now, I take my total mass of sample, 0.165 grams, and I'm going to subtract the grams of hydrogen and the grams of carbon. Whatever's left from my sample that's not carbon or hydrogen is going to be oxygen. So I'm left with 0.0366 grams oxygen. Again, don't worry too much about sig figs here. Next step. I've got grams of all these guys that are in my valproic acid sample, but now I need to find moles of these guys. Okay, so I'm going to do that. 0.0184 grams hydrogen. This is, you know, easy peasy. Gives me 0.0184 moles hydrogen. 0.110 grams of carbon. I'm going from grams to moles. 2.0 grams, 1 mole. Gives me 0.00917 moles of carbon. And for moles of oxygen, 0.0366 grams of oxygen, 16.0 grams of oxygen, 1 mole oxygen. I think let me just make sure that this is right, it's 366 divided by 16. Okay, that's close enough. 0.002. When I made my other key, I used a slightly different number, but that's okay. This will be totally fine. 228 or 229 moles of oxygen. Okay, now what I'm going to do is divide by the smallest number, which in this case is the oxygen, 0.00229, 0.00229, and we're doing this because we're interested in proportions, because that's what empirical formulas are. 0.0184 divided by 0.00229. All right, that gives me 8.03. Do the other one, 0.00917 divided by 0.00229. 4.00, and this of course is 1. So I have C4, H8O for my empirical formula. If you wrote H8C4O or some other like combination thereof, totally fine. But this is kind of what the standard would be for writing that, just in terms of, you know, chemistry circles.